In 6.2, you guys will be introduced to the definite integral, and I am going to use what you already know about Riemann sums to help introduce the definite integral to you guys. So take this graph for y equals radical x. Let's say we want the area underneath the curve of y equals radical x from x equals 1 to x equals 4. And I have three rectangles here. There are three left endpoint rectangles. And if you notice, if I use these three rectangles to approximate the area underneath this curve, we have an under approximation. So these three rectangles do not cover all of the area for the region from 1 to 4. We're excluding some portions here. So can you think of a way to get a better approximation? How can we get a better approximation? And let's say we draw more rectangles. So our approximation gets better the more rectangles we create. Okay, so we kind of closed that gap there. We kind of closed, the region that wasn't covered is covered a little more now. So our approximation gets a little better there. And then what happens if I then draw more than that? So the approximation gets better as we create more and more rectangles. Notice that that's even better than the three rectangles that we started with. Okay? So can we just keep going? Can we just keep creating more and more rectangles? Yes. Go ahead and copy that down. So as n approaches infinity, quick reminder, n represents the number of rectangles. As n approaches infinity, so as the number of rectangles approaches infinity, the accuracy of the estimate improves, which means we get closer and closer to the exact area. And I'm going to use this website, GeoGebra, to help explain, get a better visual of what's going on. So here using GeoGebra, I have the equation or the graph for y equals radical x, and this is more or less what we had in my previous slide. So three rectangles, left endpoints, and so I'm going to use this to kind of create more rectangles. So far I have it set for n equals 3, and when we have a left endpoint with three rectangles, the approximation is approximately 4.1463. Okay, so there it is with 4. Also notice that the approximation changed. Okay, now we have 4.2801, 5 rectangles, 6 rectangles. Notice also look at the figure there. The more rectangles that are being created, the closer we're getting to filling in the region that we want. Okay, right now I'm at 37 rectangles. Okay, so the more rectangles that we get, the more we're covering that region. And if we look at it in terms of sigma notation, remember this notation, this was used on Monday's video when I introduced Riemann sums. Go ahead and copy this down. Obviously you didn't have to copy the that little video or the GeoGebra stuff. I didn't expect you to copy that down. But so what we have here is, remember that the sigma as I equals 1 goes to n of f of c sub I times delta x. Remember that this represents the height and this is the width. Okay, area, height and width that represent the area, or that's used to represent the area for the rectangles. Now this is a similar notation that we used on Monday's video, but now I'm saying that we want the limit as n goes to infinity. Okay, so the limit as the number of rectangles goes to infinity. Okay, and we're going to take the sum of all of these, the area of all of these rectangles, and that will give us the best approximation, or the accurate area underneath the curve here. And that sigma notation, the limit as n approaches infinity of the sigma from I equals 1 to n of f of c sub I times delta x, is what pretty much is the definite integral. This right here is the definite integral. Okay, so this should be pretty familiar notation, except now we have a and b. Now we have what is called a lower limit and an upper limit. Okay, so a is the lower limit, b is the upper limit. So this sigma notation is pretty much the summation. So the relationship here is that the sigma notation is this integral sign. We have that f of c sub I, we said that's the height, that's f of x, and the delta x is the dx. Okay, so we're not going to be focusing on this. Hopefully this is not, worrying you guys. This leads to this, and this is the main focus here. So this will be the main focus. Okay, and add this to your notes. The definite integral is a number. Okay, we are going to get a number when we use the definite integral. Area is one of the interpretations of the integral. Okay, so try to think of another interpretation for the integral. So think about it, and I will give you a hint. We covered it at the end of first semester. When f of x is less than 0, the definite integral gives the negative of the area. And hopefully you're not thinking that area can't be negative. Think of it more as the negative interpretation of area. If we want the geometric area between the curve and the x-axis, take the absolute value of the result. Okay. So pretty much what I'm saying is, let's say I start creating rectangles on, so let's take this function for example. Okay, and from A to B, notice that this first part, this first region is underneath the curve of f of x, or x. So let's say I start drawing rectangles. Well, my y's, or the height, is going to be negative. See how Remember, below the x-axis we have y outputs that are negative, and pretty much anywhere here we're going to have negative. Negative times a positive. The negative height times a positive width or base will give us negative. Up here it's still positive. And I'll end the video with some rules for definite integrals. So the first one is called the zero rule. Let's say we have an integral that goes from a to a. So from the lower limit and the upper limit are the same value, we get 0. That's the answer, 0. Think about why that might be true. And if you don't quite understand it, you can ask me in class tomorrow. Number 2 is called the additivity. So if we take the integral from a to b of f of x dx plus the integral from b to c, notice that this second integral that's being added starts, the lower limit is the upper limit of the previous one that goes from b to c. Then we get the integral from a to c. We get the integral from a to c of f of x dx. Third one is called order of integration. Let's say we have the integral from b to a of f of x dx. However, we want to flip it around. So we flip it to the integral from a to b. That's fine. However, you have to then take the negative of it. So the negative integral from a to b of f of x dx. The next one is a constant multiple, just like we've seen too many times already in this class. If we have a constant, we can go ahead and take it out and worry about it, integrate without the constant in there. And then finally we have the sum and difference. That's another one that we've seen too many times in this class. If we're integrating from a to b f of x plus or minus g of x dx, then we can just kind of break them up into their own integrals. So the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And we'll look at more examples in class. I just really want to put out there the notes for you guys, and we'll do examples in class. That'll do it for this video.